Hello and welcome back to Physics Demystified. Thank you for joining me again. This time, as promised, we're looking at what you can find inside the atom before going on to look at some particles. We'll be looking at 5 different subtopics. These are as follows: inside the atom, which we're doing today, stable and unstable nuclei, photons, particles and antiparticles, and particle interactions. That's the next few videos covered. So let us start straight away on the first of these, inside the atom. So some of this is going to be familiar, some of it will challenge your current understanding of the atom, some is going to be entirely new, but it should not prove too much of an ordeal getting to grips with. After all, you've been studying atoms for years now. You know them inside out, possibly. So in order to understand the atom, we need to look at 3 things: the structure of the atom, isotopes, and specific charge. Now, it's the last of these that will possibly be unfamiliar to you, but don't worry, we're going to make sure you fully understand specific charge by the end of this video. So then, structure of the atom. Now, the chances are you have a model of the atom that you have in mind. You've developed this over the last few years. I should think it looks something like this. There'll be a nucleus at the middle, probably, and lots of electrons orbiting around. Now, it may not be as fancy and 3D as this, but it's kind of like planets around the sun, that sort of thing. And such a model is all very well, and it's a good way of looking at things. It works. It can explain much of physics and chemistry. Not necessarily how it actually is, but we'll come on to that later. Now, atoms are small. Now, I mean really small. An atom is going to be something like 1/1,000,000th of a millimetre across. As you can see, an atom is to a human what the human is to the size of the universe on that kind of scale. Now, the nucleus is positive. It's comprised of protons and neutrons, and they're collectively known as nucleons, and it's surrounded by negative electrons. There we go. Here's a nice model of the atomic structure telling you what the particles are like. As you can see, the electron is a much smaller mass than the proton, 1/1840th roughly of the mass. The proton and the neutron have almost equal mass, and the electron has an equal and opposite charge to the proton, and the proton is neutral, has no charge. And that means that an uncharged atom has equal numbers of protons and electrons. An uncharged atom becomes an ion if it gains or loses electrons. Okay, so now we know the structure of the atom, we need to remind ourselves about isotopes. Every atom of a given element has the same number of protons as any other atom of the same element, the exact same number. You change that number, you change the number of protons, and you change the element. It's as simple as that. The number of protons dictates the element. Now, the number of protons in an atom of any particular element can be determined from the proton number, also known as the atomic number, and designated by the symbol Z. For example, carbon. Now, the Z number for carbon is 6, because every carbon atom has 6 protons in its nucleus. Uranium, however, has a Z number of 92. It's because it has 92 protons in its nucleus. However, the atoms of an element can have different numbers of neutrons. This doesn't change the chemical nature of the element. Atoms of the same element with different numbers of neutrons are called isotopes. That's what it means. For example, the most abundant isotope of natural uranium contains 146 neutrons, and the next most abundant contains 143 neutrons, but it's still uranium. Definition that you need to learn: isotopes are atoms with the same number of protons and different numbers of neutrons. Remember that, it could come in handy. Having a look at uranium 146 and 143, you'll see the total number of protons and neutrons in an atom is called the nucleon number, A, there it is, or sometimes the mass number or the atomic mass of the atom. That's because it's almost numerically equal to the mass of the atom in relative units, where the mass of a proton or a neutron is approximately 1. Now, a nucleon is a neutron or a proton in the nucleus. We label the isotopes of an element according to their atomic number, Z, their mass number, A, and the chemical symbol of the element. You'll recall this format from earlier. We can present this in generic format thus. Each type of nucleus is called a nuclide and is labelled using the isotope notation. Here we have carbon and oxygen. The example here, the nuclide for the isotope carbon-12 has 2 fewer neutrons and 2 fewer protons than the nuclide of the oxygen isotope oxygen-16. Okay, so now we've revisited isotopes, we can look at specific charge. Specific charge may be something you've not heard of before, or maybe just not familiar with. Maybe you are. Well, we're going over it anyway. It's quite a simple concept really, and it's there to provide a way of comparing different atoms. It's somewhat analogous, I suppose, in a way to density. We're now going to see how we work it out. So the first thing we need to know to calculate the specific charge of a particle is its charge and then its mass, because its specific charge of a charged particle is defined as its charge divided by its mass. So in order to calculate the specific charge, we need to know its total charge and its mass. It's then simply a matter of dividing the two values. For example, hydrogen. A nucleus of 1 hydrogen has a charge of 1.6 by 10 to the minus 19 coulombs and a mass of 1.67 times 10 to the minus 27 kilograms. So therefore its specific charge is 9.58 by 10 to the 7 coulombs per kilogram. The electron has a charge of minus 1.6 by 10 to the minus 19 coulombs and a mass of 9.11 by 10 to the minus 31 kilograms. Its specific charge, therefore, is 1.76 by 10 to the 11 coulombs per kilogram. Note that the electron has the largest specific charge of any particle, mainly down to its tiny mass. An ion of the magnesium isotope 12Mg24 has a charge of plus 3.2 by 10 to the minus 19 coulombs and a mass of 3.98 by 10 to the minus 26 kilograms. Ignoring the mass of the electrons, they make no difference. It's like calculating the mass of Earth and forgetting to add in a few tennis balls. Its specific charge, therefore, is 8.04 by 10 to the 6 coulombs per kilogram. Well, that about wraps it up for Inside the Atom. Next time we're going to be examining stable and unstable nuclei. So if you have any questions in the meantime, or comments or requests to cover a particular topic, then please do email me at the address in the description or leave a message in the comments below. Don't forget to like us, click on the bell for updates, and follow us. So until next time then, keep wondering about the universe.